So again, the question to ask yourself when you're looking at pictures like this for osmosis, ask yourself, is water able to pass through? Now, in all examples we're going to talk about, is water, that says able right there. In all examples, the answer is yes. Water is going to be able to pass. That's osmosis. Is the solute able to pass? You know, that could be a yes or a no, depending on the size of the molecule. And you know, that's a question you're going to ask yourself in lab today. Okay, it's like we have different conditions, and we're going to have like 10 groups, 5 different conditions. We're going to have some that are glucose. That's the solute, maybe at different concentrations. I think we got a 10%, 30% solution. 2 different concentrations, see a difference in osmotic draw. Oh, we're going to have some salt. We have a salt group. Okay, well, basically salt. We're going to have albumin. We're going to have, I think we have starch. Okay, so we have different things that'll be our solute. And maybe it can pass through, maybe it can. You have to have a way to test it. Like you have a beaker of fluid, and it's filled with water, of course, and you're going to immerse your dialysis tubing. An exaggeration. It's kind of clamped off at the top, and it's going to be clamped off at the bottom. And I think one of them's weighted so it doesn't float at the top. It's fully immersed. And it's going to be a solution of, you can read your protocol on how to fill this bag and pinch it off. And one of these things. So your group isn't doing all of them. Your group is doing just one of them. That's your contribution. And you gotta ask yourself, well, how do I get the data from everything else? Well, you got to wait for all your other groups in the class to finish, and we'll all report it up here. Okay, I'll get to that. But the point is, let's say, for example, you got 10% glucose in here. So you got, in addition to water, you have glucose, green balls. Probably water molecules, blue balls, they can probably pass through and get in. Question is, can the solute pass out? Okay, and you'll be able to test that because we got it all written up for you. So it's like, well, if I want to test if that green ball got out, well, why don't I just take some of this solution, grab some, test for glucose, or for whatever, okay? And you need a positive control, negative control. Your lab procedures will take you through that. Okay, I'm not going to teach it because you got procedures to read. But that's the basic idea for that. Now, to move on, osmosis is important to cells. That's why we study it in the cell chapter. Osmosis across the cell membrane can cause cells to shrink or swell, which could be bad, because if it swells too much, yeah, it'll lyse, and that's not good. And so, you want to kind of maintain it, and, well, it depends on the osmolarity of the intracellular fluid versus the osmolarity of the solution the cell is in, okay? So you have this figure in your book, which kind of illustrates the conditions that you can have for a given cell. So we're talking about cells here, but in our lab we simulate that with, instead of cell, like that's our cell, our dialysis tubing, right? So let me erase this. So OSM, as on the previous slide, means osmolarity. You remember studying molarity, moles per liter. It's a unit of concentration in chemistry, and it's the same thing here. This is just biological osmolarity. It's like a biological saltiness. And the os is for osmosis, okay, because it's the diffusion of water. And then so we have different scenarios here. Let's say, for example, in that first scenario on the figure, maybe you have a big beaker filled with a fluid. And maybe the fluid has an osmolarity of 10. You can drop a cell in there. In this example, they use a red blood cell. Okay. Well, let's say that the osmolarity is also 10 of the intracellular fluid. Okay, you're comparing the solution of the osmolarity of the solution versus the intracellular fluid of the cell, because that'll determine osmosis. The golden rule I gave you is water goes to where the most stuff is, but if it's equal, what will happen is pretty much as much water will enter as leaves. So there's kind of like no net movement. Okay, there's no net anything. There's no net gain of water or loss of water. So pretty much no net fluid movement. And, the cell ought to maintain its shape. Okay? Cell maintains shape. In that second example there, they have the cell shrinking after an incubation time. So maybe that's a scenario where they drop that cell in, and maybe it's kind of a saltier solution. Rules of osmosis say I'm going to go towards more salty, more than something coming into me. Because what's happening is, the second law of thermodynamics, order to disorder. Nature doesn't like an ordered state. It doesn't like that that's 20 and that's 10, all compartmentalized, nice and neat. It likes things to be mixed up and even. So this is trying to equilibrate with a 20. Okay? So it's losing water. It's going to shrink. So I'll say net water loss, cell shrinks. Shrivels, shrinks. However you want to put it, as shown there. Okay? And the last scenario is the solution. Maybe it's like 1. Maybe it's just like water, and you put the 10 in there. Well, again, water goes to where the most stuff is. You're going to have net gain. Cell swells. So in each condition, you consider the solution that it's in, and whether it causes this shape change. Now, any questions on that? Well, if you understand that, you're pretty much got the whole thing. This is pretty much our lab. We're just like, you're just putting it in the water. So you'd expect if there's something in there, it should gain weight. And you're going to weigh before and after, okay? You have an hour incubation. The question becomes, what do you do for that hour? Well, I'll tell you, you go to Starbucks. That's what I would do. Come back in an hour, post-weigh, and do your analysis. So I would try to get your thing in there 10 o'clock, or maybe before. Come back, you should have enough time to finish it up and report. When I was a grad student, I had long incubation times. I would walk into Westwood and watch a movie. Now, you don't have time to watch a movie, but you have an hour. You have some downtime. That's good. So solutions can be isotonic. iso means same, okay? The solution it's in, same, where the solution's osmolarity equals the cell's osmolarity. So isotonic solutions OSM equals cells OSM. That was the first one, right? This one where it like shrinks, hypertonic. Where the solutions, it's more than, hyper means more than, greater than. Or hypo, the last one. Hyper greater than, hypo less than. Just to help you remember. Okay, I'll skip over these for now. I'll ask you later in a different way. But that's basically I put this in because it's kind of like our lab, except it's not a bag, it's a tube that we clamp on both ends, so I'll just kind of skip that. Now, this kind of leads to other things, because if the solution can actually make it swell or shrink, that makes pressure build up inside if it's like swelling, or if it's deflated, there's no pressure. So this leads to different terminology, osmotic pressure and hydrostatic pressure. So tonicity, the things I just defined there, these three things, that's the ability of the solution to alter the water volume of the cell. Right? Because, well, the first one, there was no change. But hyper, we saw that cell shrinks, cell swells in the hypo. So it's the ability of the solution to kind of change it. But then when you do that, say for example, if you swell, you build up pressure inside the cell. And if you're sucking fluids into you, that's something that's called osmotic pressure, osmosis. Water is being taken up by the cell. So when you see that term, make that connection. The osmotic pressure, it's kind of counterintuitive a little bit. The ability of a solution to draw water into something as a result of its solute concentration. I'll rephrase it. The ability of a cell, it could be something else. We're talking about cells, to draw water into itself. Hydrostatic pressure opposes osmotic pressure. Hydrostatic pressure wants to push fluids out of a cell. Okay? It's like the back pressure exerted by water against the membrane. Pretty much it's the opposite of osmotic pressure. If osmotic pressure draws water into you, hydrostatic pressure pushes water out of you, basically. So I'll say it opposes osmotic pressure wants to push fluids out of the cell. How I think of it in this lecture, I think hydrostatic pressure results from osmotic pressure. Because if you have an ability to draw water into you, you're going to be full. You're going to be swollen. Therefore, you're going to have a lot of pressure in you, and that's going to push the stuff right back out. Okay? So just to give you an example, let's live by the concepts. Beaker 1, 2, 3, and they're all filled with water. Let's make it all the same, 10. That's the osmolarity of the solution. And let's make this all hypo. They're all going to be hypo to different degrees. So let's drop the first cell in. Let's make the intracellular fluid 20. That makes it a hypotonic condition. Let's make the next one 100. Let's make the last one 1,000. The question I have for you is, well, which condition has the highest osmotic pressure? I guess you call it A, B, C. Which condition has the highest osmotic pressure? Now here's what they have in common, A, B, and C, before we answer the question. They're all going to have net flow in, right? All of them. Maybe this one a little bit more. Maybe this one a little bit more than that one, but this one will have the most in. So C is the answer. It has the highest osmotic, it has the most ability to draw water into it. Now, as a result of C, or A, or B, the cell's going to swell in all cases. As a result of cell taking on water, right? I'll say swelling. You're gradually increasing the hydrostatic pressure as it swells. There's a process here. Sweating. As a result of swelling, the cell's hydrostatic pressure gradually increases. Now remember, hydrostatic pressure is opposing the osmotic pressure. So I guess one of two things could happen. You could swell to the point where hydrostatic pressure is so big inside, it's like water can't come in anymore. So you just stop swelling. Or the cell could burst. I guess there could be a third one. It doesn't ever burst and you just start pushing water out. Well, anyways, here's the rule for the osmotic, hydrostatic, just to boil it down. If hydrostatic pressure is greater than osmotic pressure, there's going to be a net fluids out. If hydrostatic pressure is less than the osmotic pressure, net fluids in, which is all three cases for my example. If they're equal, there's no net flow. So it's kind of the same thing, it's just using different terms, hydrostatic versus osmotic. If you swell, you build up hydrostatic pressure in you until you burst or just start pushing fluids out. Okay, so those terms are used to talk about osmosis too. And then they come up a lot, especially when we talk about blood pressure. Yeah?
So what determines if the cell is going to lyse or if the cell is going to try to even out its,
Well, it just depends, I would say it depends how permeable it is to water. If it's less permeable to water and it's taking up a lot of water, it's going to burst eventually. If it's very permeable, got a lot of holes in it, it'll just let the water out. Yeah. Okay, good question. Any other questions before we look at the U-tube? Okay, it's the original U-tube. It's literally a U-shaped tube, and it's easy to illustrate osmosis rules with it. In this scenario, I believe the water can pass through the selective permeable membrane as well as the solute. See, when you start, it's like less concentrated on the left. But if you allow water and solute to freely pass, eventually it'll equal out. And notice that the level not only has concentration equaled, volume is equal when the solute can pass through. If it's a case where only the water can pass through, then, well, the concentration will equal out, but the volume will be unequal. Okay? That's kind of what happens when water can pass, but not the solute. So I have a couple of questions here. I'm going to show it to you here. Then I want to like do an interactive thing. It's not a quiz, but it's one way I do as a class feedback thing for myself to make sure I know you're getting it. Well, the question is at the top, which cell, A or B, had a higher osmotic pressure to start with? You can see what happens as a result. Shrinks, swells. Okay, that's one thing I'm going to ask you. Think about that for now. Don't answer it now. Just okay. And then, kind of a follow-up question to that, which cell, A or B, ends up with a higher hydrostatic pressure? This or that. If you have a phone or other mobile device, get it out. We're gonna. I use something I use for class interaction. It's called Kahoots. It's an online quiz. Play. Classic. It's not for your grade, just for fun. So if you don't have a phone or a tablet, just don't worry about it. Have fun, no music. What you do to join, open up a web browser, go to kahoot.it, and just enter in the PIN. And when you do, you'll be asked for a nickname. You don't have to put your real name, but nothing profane. Just push. It's not like I know you're here. I usually wait till like high 20s, then I'll start, because I know not everyone has a phone with them. I'll ask you some osmosis stuff.
So just to kind of recap, because I'm a little confused for hypo and then hypertonic. So if the osmotic pressure is low, then it's hypotonic. No, it's hypertonic, right? Because it swells.
If it swells, it means the osmotic pressure was high.
Okay.
If it shrank, it's probably low, yeah. I got 19, anybody else? I like to do it for stuff like this where it's like, I think you got it, but I'm not sure. Because I always get surprised, like, wait, you didn't get that? I thought everyone got it. So this is kind of one of the ways I kind of check right after I teach it. You can continue to join at any time. Like I said, it's just for fun. It's not part of your grade. Let's start. Osmosis questions. Question is loading. Which condition is hypertonic? Choose A, B, or C on your device. I gave you a minute. It's plenty of time to think about it. Which is high. And sometimes I make mistakes when I set these up, but yeah, but which one is it? Well, time's running out. What do you guys think? Okay, well, we'll see. I should have put B if I set this up right, yeah. Okay, some of you did miss it, right? It's not, well, let's just do the next one. You'll straighten yourself out. But that's a good ratio for students. And it did a score. I don't keep score. It scores you based on how fast you answer and how many you get right, and stuff like that. So the hypotonic situation. Yeah, C is correct. Okay, you guys are doing pretty good there. Which condition is the solution isotonic? Easy one, right? What's left? Sometimes it is easy. There's always one student that wants to drive me crazy, right? You should have put A. Which cell, A or B, had a higher osmotic pressure to start with, knowing that one shrank and one swelled? Remember, osmotic pressure is the ability to draw water into you, like a sucking pressure. Okay, good. It is B. Yeah, if it's swelled, that means you had a stronger ability to draw water into you. Next. Which cell, A or B, ends up with a higher hydrostatic pressure? How do we B again? It's B again. No. This is where, okay, this is good for me because I see most of you missed it. This is why I like to do this. Why is it B? Ends up. Now, the way I phrase the question, which ends up with a higher hydrostatic pressure. Hydrostatic pressure is the pressure in the cell and the fluid pushing against the cell wall. Okay, that's the hydrostatic pressure. Osmotic pressure is you suck fluids into you. Hydrostatic pressure is you push against it. So if your bubble's about to burst, this has a higher hydrostatic pressure. This ends up with a higher hydrostatic pressure. It had a higher osmotic pressure to start with, but as it swelled up, it ended up with a higher hydrostatic pressure. This one has no hydrostatic pressure. It's all shriveled and deflated. Deflated, no hydrostatic pressure, a bubble about to burst, lots of it. Any questions on that? Yeah, so I'm glad I caught that. Maybe you did it where, oh, it was B the last time, so it's gotta be A this time. Maybe that was it. Don't do that. Don't go based on, like, witchcraft. Oh, it was A, now it's B. It can't be B again.
Hello, money.
We like to do it based on knowledge. Okay. But you know, there are strategies to take tests, so I get it. All right, so you know, this is kind of what we're doing in lab today. So let me kind of explain. This lab is a little unusual. I put 2 docs on Canvas. Now, one is the procedures, which if you forgot, I put a pile over there. Really holding your hand today. If you forgot gloves, I put a box of gloves out there too. If you forgot goggles, I even have goggles under the hood there. So I'll hold your hand for the first couple of weeks here, but eventually bring your own PPE, right? Okay, let's see here. So one doc is the procedures. Okay, this doc you need for the lab. Use it to take down the data. Okay, collect data. But you don't turn it in. It's just the procedures. I don't need to see it. But you do need it. If you look on the most important table is on the last page. Reporting data, all 10 groups, and you're only one of them. So everyone has to report their group. Usually what I do, just to show you, I'll just get it up there right now. Osmosis lab. Yeah. Go over there. You can help yourself later. It's no problem. So what I usually do, I just get my Word doc out. And I just like kind of go like right here. That's pretty good. And I just pull the screen up. You do the lab, you incubate for an hour, come back. Well, before you incubate, you pre-weigh and get that up here. Or you can just do it at the end, I don't care. Then you incubate, go to Starbucks, get the post-weigh, and do your analysis. Did the bag gain weight, yes or no? It probably should. Did the solute pass through? And you have to test that too, yes or no. And you got to wait for all 10 groups to just right up here, okay, directly. Just sit around and wait if you're the first one done until all 10 groups provide. And boom, take that data, you can go home, and you should be able to write this up pretty quick in the other doc that says, Osmosis lab write-up. And answer these questions, you just fill in the text box there.
I was just about to ask you that.
Yeah, so basically it says submit to, you submit it to Canvas. Submit to Canvas. So the write-up part is a different doc. It's not, I made them 2 docs, so there's no confusion. Which part do I upload? The one the doc that says write-up. Submit to Canvas. It's just file upload. And I gave you to this Sunday to do it, I believe. Okay? Upload by Sunday. I mean, you do this, if you know what you're doing, it should take you like less than an hour. It's not hard. That's the write-up. Put this back there. Okay, well, I'll get this back to where it was. I'm done talking. You guys have any questions for me, you can ask me during the lab. Now, in terms of groups, I'm going to let you guys form your own groups. But I would like to know who you're working with. So I'm going to erase this, so you guys got it? it should be, since we have 10 groups and there's about 35 people, it should be 3 people or 4 people per group. 3 to 4 per group. There's going to be group 1, group 2, 3, 4, 5, 6. So you have to be a little social. You might actually have to introduce yourself to someone. Hey, can I be in your group? And if you have trouble finding a group, I can help place you. 3 to 4 group. Go ahead, decide. Sign up now. Which group you're in. That will determine what you choose. Right? You're all over there. It's clearly labeled. Go ahead, get started.
Do you guys have 3 people? You want to do group 2? Oh, they have things over there. Yeah, so, hey, David, one of the guys, I've dated, I've You can go sit at my desk. I'm gonna go sit at my desk. Yeah. Oh, I know, but they didn't have an extra person.
Oh, he's still going. Do you want me to stop the video? Or is it